So in our last video, we solved for the truss on the left and we drew a free body diagram. We didn't solve for the whole truss. We didn't solve for the actual magnitudes. But we did figure out which members would be under compression and which ones would be under tension. And we know which forces will cancel out which. And since we solved for a free body diagram for the 200-pound example, let's go ahead and get rid of it. And let's move over the 500-pound example, which is the same example, just with 500 pounds to the right instead of 200. And let's do the same thing. Let's solve for this one. And so we have upward reactionary forces at both Ray and Rudy, our roller and our pin, I should say. But our pin also has an X component that runs parallel to our truss, and since force of B is going to the right, I already know this is going to be going to the left to cancel it out. And we'll call it Rax, or reactionary force A in the X direction. And we'll call this one Ray, or reactionary force A in the Y direction. We'll call this one Rudy, or reactionary force D in the Y direction. And just like before we draw our free body diagram, let's solve for our reactionary forces. And in this video, it'll be very clear why. So we'll say the sum of all forces in the X direction equals 0. Well, that's equal to Rax going to the left. And we know it's going to the left because this 500 pounds is going to the right. And we can set our leftward forces equal to our rightward forces. Therefore, we know Rax equals 500 pounds. And we'll do the same thing. We'll say the sum of all forces in the Y direction equals 0. And that's, we got Ray and we got Rudy. And we've got 600 pounds downward. And since we know 600 pounds is going downward, we can assume that Ray and Rudy are going upward. Therefore, I can say that Ray and Rudy combine to cancel out and therefore equals 600 pounds. And to solve any further, we need to say the sum of all moments equals 0. And just like before, we have a moment at D. It's going up and then towards the pin, which is to the left, which makes it counterclockwise. And then we have a force at C going down and then towards the pin, which is to the left, which is clockwise, and we'll call that moment C. And then, of course, we got this force of B applying a moment, and it's going down and then towards our, or I'm sorry, to the right and then towards our pin, which is downward. And that's also clockwise. So we can say moment D and moment C and moment B all combined equals 0. And since we know which ones are counterclockwise and which ones are clockwise, we can assume our counterclockwise forces, or I'm sorry, moments, will cancel out and therefore equal each other. And I'm sorry, this isn't moment C, this is moment B. And that means that this one down here is also moment B. But then we can rewrite these to say, well, moment D is force times distance. We don't know what the force is for moment D. It's Rudy. But we do know the distance the force multiplies by, which is 8 and 24 from the pin, which is 32. We can set that equal to moment C, which has a force of 600 pounds, multiplied by its distance from the pin, which is 24 feet. And that's added to moment B, which is a force of 500 feet, multiplied by its distance from the pin, which is this perpendicular distance of 12 feet. And so I can simplify this equation by typing it in. I'm going to type it in exactly as it's written. So 600 times 24 plus, parentheses, 500 times 12. And we get 20,400 simplified on the right, which is equal to moment D, which we're calling Rudy, times 32. And to find out what Rudy equals, we'll divide by 32, feet on both sides. And so we'll just type that into our calculator, the answer divided by 32. And we get Rudy equals 637.5. So then we can take this equation here and plug in Rudy, and we get Ray plus 637.5 pounds, which we just said was Rudy, and we set that equal to 600 pounds. And so to solve for Ray, we'll subtract 637.5 on both sides, And you might notice that's bigger than 600. And so what does this mean? Well, this means Ray is actually equal to negative 37.5 pounds. And if it's negative, if we expected it to go up and we got a negative number, what it really means is it's truly going down. Anytime you expect a direction and you get a negative number, it means it's going the opposite direction, because math. And this is why it's so important to solve for your reactionary forces before you start drawing your free body diagram. So normally Ray is going up, but in this case, this sideways force is so strong that it pushes all of the weight to the right, so much that the pin actually has to pull it down to keep it from lifting up and flipping over. So this 600 pounds actually combines with Ray to cancel out Ricky. And then of course we've got Rax, which is 500 pounds to the left. And remember what this pin does. This pin's job is to hold the bridge in place so it doesn't fly away, so it doesn't blow to the right, or it doesn't flip over with this force trying to literally lift A up. But from here we can draw our compression and tension forces. We know that C has to be pulled up with 600 pounds of force since it's being pulled down with 600 pounds of force. But we'll save calculating what the actual tension and compression amounts are for the next lesson, and just settled for knowing that it's tension positive. And then we know D is being pushed up, so we need a downward force. And this downward force is going to have a Y component that cancels out 637.5. Which means it needs to be much bigger than 637 in order for its Y component to be the same. Again, we'll talk about all that in the next lesson. For now, let's just know that the forces all cancel out and equal 0 at every joint. So this is CD, member CD, and I know it's going to the left at D because it has to cancel out this rightward force of BD. So that means it's under tension positive, because if it's going to the left at D, CD has to be going to the right at C. Well, now C is being pulled to the right, so we need a leftward force. And that's provided by member AC. And if it's pulled to the left at joint C, that means AC has to be pulled to the right at joint A, which makes it a member under tension or positive. And now for the last bit, and this is again why it was so important that we calculated our reactionary forces before we drew our free body diagram. And that's because if we look, well, there's a leftward and a rightward force, and we don't know which one is going to be canceled out. So I'm going to ignore that. I'm going to look at my downward force, because we only have one of those. So we need an upward force that will equal it. So this Y component of AB will cancel out that 37.5 going downward. But if it's going up and to the right, that means it's going down and to the left, which means in this case, AB is tension positive. So hopefully now you see how these extra sideways forces can affect your free body diagram, and why it's so important to calculate your reactionary forces before you draw your free body diagram. And the last thing I want to leave you with is that these numbers will equal, AC will equal CD. Because it has to, because C has to be pulled to the right as much as it's pulled to the left to cancel out to equal 0. And in our next lesson, we will learn how to calculate those numbers to prove that they cancel out.